Hello, welcome to this lesson. In this lesson, we will learn how to eliminate arbitrary constant from any given recurrence relation, and we will discuss this by solving examples. Okay, so now, first example, this is our recurrence relation. Okay, an equals to we have to find a recurrence relation whose solution is given by an equals to a times n factorial. Okay, so our arbitrary constant here is a, so we need to eliminate our arbitrary constant. Okay, so let's find the next term of this solution. Okay, so the next term will be a of a subscript n plus 1, so we just replace n by n plus 1. Okay, so when we do that, we obtain this. Okay, and a times n plus 1 factorial is just the same as, because when you have n plus 1 factorial, it's just like n plus 1 times n factorial. For example, when you have 6 factorial, 6 factorial is the same as 6 times 5 times 4 times 3 times 2 times 1. Okay, but 5 times 4 times 3 times 2 times 1 is the same as what? 5 factorial. So this is just like 6 times 5 factorial. So it's just like this. Okay, you just reduce this by 1. So when you have n plus 1 factorial, it's just like n plus 1 times n factorial. Okay, and you can rearrange this as this, but don't forget a times n factorial is given by a subscript n, so we replace a by n factorial by what? A subscript n, and we get this. Now we have obtained a first order linear recurrence relation of degree 1. Okay, first order linear recurrence relation of what? Degree 1, and there is no arbitrary constant. Okay, let's move on to the next example. Okay, we have to find a recurrence relation whose solution is this. Okay, so for this particular solution, we have two arbitrary constants. Okay, that is a and b. Okay, and we also have to find a particular solution. So we are given initial condition a naught equals to 1 and a1 equals to 15. So first of all, let's generate a recurrence relation, okay, using this solution. So first of all, we find the next term, that is a subscript n plus 1. So we just replace n by n plus 1. When we do that, we obtain this. Now after expanding this equation, we obtained this. Okay, then maybe you can remove bracket by multiplying through by 3 exponent n plus 1. When we do that, we get this. Okay, now we want to find a way to eliminate one of the arbitrary constant. So first of all, we rearrange this. So we rearrange the first term, the third term, and the second term. Okay, so when we do that, we get this. Okay, but don't forget 3 exponent n plus 1 is just like 3 times 3 exponent n, then you multiply by a, you obtain this. Okay, so for you consider the first two terms. On the first two terms, you realize that this 3 is a common factor and 3 exponent n is also a common factor. So you factorize 3 out. When you factorize 3 out, we are left with it as what we have here. Then here on the other side too, we have what? Bn. Then you can also factorize 3 exponent n out. But don't forget, a times bn all multiplied by 3 exponent n is given by a subscript n. So we replace all of this. We replace all this by a subscript n. And when we do that, we obtain equation 1. Okay, now we have eliminated one of the arbitrary constant. Okay, That's we have eliminated A, so we need to eliminate B as well. And how do we do that? We need to find the next term, okay, of the recurrence relation. So we find A of n plus 2 is A subscript n plus 2. Okay, so just like A subscript n plus 1, where we replace n by n plus 1, the same thing applies to A subscript n plus 2. We just replace you can even replace it in equation 1. Yes, it's in equation 1. A subscript n plus 2 is just, you are just moving one step. Okay, so it's just like adding 1 to n plus 1. Okay, so when you do that, the right hand side will be A subscript n plus 2, and this one, A times 3, A 3 times A subscript n will be what? 3 times A subscript n plus 1 plus B times 3 is subscript superscript n plus 1 will be B times 3 superscript n plus 2. Okay, and you see, this can also be written as this. Okay, and when we factorize 3 out, we obtain equation 2. Now, from equation 1, when we make B times 3 exponent n plus 1 the subject, we obtain A subscript n plus 1 minus 3A subscript n. Okay, so you see, from equation 1, our B dot 3 exponent n plus 1 is just like A n plus 1 minus 3an. Okay, so we can now substitute this into our equation 2. Okay, so when we do our substitution, we have this. Okay, so when we simplify, realize that these are like terms, so we obtain 2A subscript n plus 1 minus 3A subscript n, all multiplied by 3 equals to the left hand side, and this is given by this. And we can rearrange this equation by this. Okay, so this is actually the recurrence relation, and it's second order linear recurrence relation of degree 1. Okay, second order linear recurrence relation of degree 1. Now for the particular solution, we're given A naught to be 1 and A1 to be 15. Okay, so A naught, that means n is equal to 0. So when we put n equals to 0, we get this, and you obtain A equals to 1. Then A1, that means n is equal to 1. So when you put in 1, you obtain this, and when you simplify, you get B is equal to 4, and therefore the particular solution is given by this. Thank you.